The goal of this lesson is to design a coffee cup with a handle. We will use an interesting idea called a sphere sweep in order to do so. In order to understand how a sphere sweep works, I designed a bunch of files here. The first file I included the grid so that we can see what's going on. And I already set up a light source and camera. Now we're going to place two spheres on that grid, one at the origin and having radius 0.2, and another one 2 units to the right, having radius 0.2. And let's run that and we'll see the two spheres. There they are. Now what a sphere sweep does is it moves the first sphere to the position of the second sphere, and it keeps track of the movement. So let's take a look at that. So if I go to my second file here, what I did is I replaced those two spheres with what's called a sphere sweep. Now I told it to have a linear spline. A spline is a path, and the linear means it's going to be a straight line path. The number 2 tells us that there are two positions, a starting position and an ending position, and both of them have spheres of radius 0.2. So what's going to happen is that first sphere we had before is going to move from the origin to the 0.2 units to the right, and its movement is going to be traced out. Take a look at this. There you go. So the sphere started here, and it moved along, and it ended up here. Now what's interesting about this is if you change the radius of one of the spheres, say the one at the end, move it up to 0.6 units instead of 0.2, then you get the following picture. So the sphere starts out with a radius of 0.2 and it gradually increases its radius until it reaches 0.6 at the end. All right, that's it for a linear sphere sweep. Now there are two other types of paths that we could use. One is called a cubic spline. Let me change this to cubic. If I try that with our points that we have, we get an error message because for a cubic spline you need at least 4 points. So let me go back to the linear spline and put 2 more points in. So change this number from 2 to 4, and then we'll put it back to the cubic. Now let's put a starting point to the left of the origin. Let's say we put the starting point at -2 to the left there, and give it the same radius 0.2, and put one to the right. Let's say we put it at 4, and give it the same radius of 0.6. Now if I keep it as a linear spline, you'll see the following. Okay, we have to move the camera back so that we can see better what's going on. Let's see, maybe move it back to 40 units back. Okay, it looks like a baseball bat. So I have a sphere at -2 with radius 0.2, a sphere at 0 with radius 0.2, then a sphere at 2 with radius 0.6, and a sphere at 4 with radius 0.6. So with a linear spline, we get this picture. If I change this from a linear spline to a cubic spline, you'll see what happens in a moment. Cubic. And we run it. And you see the starting point at -2 and the ending point at +4 no longer show up. So those are what's called control points, and it starts drawing the picture from here to here. Now another type of spline is called a B-spline. That stands for Bezier spline, mathematical fitting of the curve. If we do that, we get the same kind of picture as we got with a cubic spline. So let me show you a comparison of these three splines. I moved them over so that, or up and down, so that you can see all three of them at once. So here is the linear spline, here's the cubic spline, and here's the Bezier spline. You'll notice something about the B-spline, and that is that the starting point here is shifted over a little, and same with the ending point, as compared with the cubic spline. We will see later that the B-spline is the best kind to use if you want a nice smooth transition from one point to another. Now let's use 5 points. I put some spheres in here. I put a sphere at -2, left 2, and up 2, radius 0.2. All of them have radius 0.2. A sphere at the origin, as we had before, a sphere 2 to the right, as we had before, and a sphere 2 to the right and 4 up, and then a sphere at the origin, or 4 up from the origin, and then the final sphere is in the same position as the beginning sphere. Actually, I don't need this one. I'm just going to redraw the same sphere twice there. So I place the spheres here. So there's one at the origin, there's one 2 to the right of the origin, there's one 4 up from that one, there's one 4 up from the sphere at the origin, and then a common sphere at this point here, which is 2 to the left and 2 up. Now, we're going to do that with the splines. So what I did here is I did a sphere sweep with a linear spline. We have 6 points there. That last point is repeated at the beginning and at the end. And so if we run this, we see the following configuration. So we started here. No, actually we started here. And then we went to the origin, then we went over here, and then up, and then over, and then back to this point. That's what happens if you use a linear spline. Now, let's look at the other types of splines. If we change it from a linear spline to a cubic spline, with the same points, we get the following picture. Now, something peculiar happens here. We get it chopped off here and here. I don't really know why the cubic spline does that, but sometimes that happens. That's why I don't like to use the cubic spline. If we change it to a B-spline or Bezier spline instead of the cubic spline, then we get this picture. And notice how it curves around rather gracefully. Remember, there was a sphere here. Also notice that the starting sphere at the origin is no longer at the origin. It's shifted up a little because this sphere that we had over here is pulling it in that direction. So we'll see that the B-spline or the Bezier spline is usually the best one to use if you want a nice curved object. Let me show you a comparison of those three. I put all 3 of them in here and I moved them over so that we can see what's going on. So here it is with the linear spline, and it shows the starting and ending sphere. Here's with the cubic spline, it no longer shows the starting and ending spheres. And here it is with the B-spline. Notice how the B-spline brings it inwards because of the starting sphere over here somewhere. Now let's see what happens if we change the starting sphere's radius to 0.6. And likewise for the ending sphere's radius to 0.6. Here I just have the linear spline. Kind of an interesting shape. So the starting and ending spheres have a radius of 0.6, and then they travel down to radius 0.2 as it goes around, and then increases again to radius 0.6. Let's see what happens if we change it from a linear spline to a cubic spline, which is what I did here. Again, you notice that there's a little bit of slicing here. I'm not sure why that happens, but cubic splines are kind of strange that way. If we change it to a B-spline and run it, then we get something more interesting. This is beginning to look like a handle to a cup. If we chop it off somewhere here, we might be able to use it as a handle to the cup. Remember that starting and ending sphere is over here, 2 to the left and 2 up. And it also has a bigger radius. So that's the effect of changing the radius on each of these. Let's take a look at these things together. So I put all 3 of them here and moved 2 of them over so we can see what's going on. Here's the linear spline. We start with a bigger radius, 0.6, go down to radius 0.2. Here's the cubic spline. We have that radius 0.6 here, which pulls this in a little bit. And notice that the B-spline curves inwards. The starting and ending points are moved up a bit here because the sphere over here, that big sphere, reference sphere, which is controlling the whole shape of this curve, is pulling it inwards this way. So we'll be using the B-spline most of the time. Now let's go back to our linear spline. Let me show that again. And we're going to add another point out here. Let's say 3 units to the right and 2 units up. So we'll change the number of points from 6 to 7 and add another point in here. Let's see, 3 units up and 3 units to the right and 2 units up. And let's see what that looks like. There it is. So I added another sphere right here. So it starts here with a big sphere, goes down to a radius 0.2 sphere, continues around this path, and goes to the big sphere at the end. Now watch what happens if we change it from a linear spline to a cubic spline. And so we've bent this handle out a little bit. Notice it's a little bit irregular here. That's why I don't like cubic splines. Let's change it to a B-spline and see how that looks. Much better. So you see we can change the shape of that handle a little bit, make it a little more roundish and have it bigger at the beginning points. And that's the good idea of a cubic spline. Let me compare these. I believe I have that file here somewhere. Yes, here it is. I put all 3 of them in there and moved the camera back so that we can compare them. And you see the first one here is the linear spline with this extra point here. Here's the cubic spline with this extra point. Notice the cubic spline does start at the second point and ends at the second to last point. The shape is not exactly what we'd like. The bending isn't so good. But if we go to the B-spline, then we get a very nice shape, and notice the starting and ending points are pulled in somewhat, and this point over here makes a nice even curve. So we're going to do something like that to make a handle for a coffee cup. What I did here is I took some graph paper and I drew a picture of a coffee cup, which I have in my kitchen. I measured it carefully. I noticed that if it's about 4 units wide, then it's a little bit taller, about 4.75 units tall. I also noticed that the outside of the handle is about 2 units over from the coffee cup at its maximum point here. Since we're going to use a B-spline to approximate that curve, I extended the curve inside the cup so I get a better picture of how it ought to look. And then I placed a starting point and an ending point for the B-spline. I put some points inside. We're going to make it a little bigger at these points, and then it's going to get smaller as we go around. So I put these points on my picture, and then I had to assign coordinates to them. I estimated the coordinates of those points. This is pretty close. There are actually 7 points there. The 2 in red will not show up on the B-spline. But if I put in a B-spline for this handle, it ought to look about right. Now notice I'm going to put the handle going inside the cup a little bit. We could always chop it off by doing a difference of something, but I'm not worried about that right now. It just depends on how we look at the cup. So here's how I decided to do the handle. I use a B-spline with those 7 points. And I started with a radius of 0.8 at the beginning and ending points, and tried a radius of 0.3 for the points in between. Let's take a look and see how this looks. Okay, that looks pretty good. So if we put the cup somewhere around here and attach that handle to it, we should get a pretty good picture. So what I did here is I put in the cylinder that represents the cup itself without the handle, and I put its base point at the origin, and I made it 4.75 units tall, and I gave it a radius of 2, which means the diameter is 4, and then I kept the handle there too. So let's take a look and see if the handle fits the way we want it to. Ah yes, looks really good. Now remember, this handle goes in the cup somewhat. I could make it an open cup, but better yet, I'd like to carve out a piece here. So let's see what we can do. Before we carve out a piece, let's combine the cup and its handle and make it into one object. The way you can do that is to put a union statement. That's POV-Ray's method of making several things into one thing. You type union and put a beginning bracket there. Let me move that over a little bit. Whoops. And close the bracket at the end. So after we do the cylinder and, let's see, end union, combine the cylinder with the handle, then we should still see the same cup. Yeah, it didn't really change anything as far as appearance is concerned, but I wanted to combine those and make them into one object so that I can carve out a cylinder inside the cup, given an inside or an opening. So let's put an inside cylinder that we will take away from the cup. I put it having a base point a little bit up from the bottom of the previous cup, and made it a little bit taller, 4.9 units instead of 4.75, and I gave it a radius of 1.8 instead of the 2, which was the radius of the cup. Let's see how this looks. Now what we want to do is subtract that inside cylinder from the cup. So in order to subtract it, we will do the difference. That's why I had to make a union of the cup and its handle. So before the word union, I put the word difference. And an open bracket, and then at the very end, I want to subtract that cylinder I just put in. I end the difference. So close bracket, and let's say end difference. Let's see if I did that right. Ah yes, so there we have it. We carved out the inside of the cup and they gave it a white color so that it stands out a little more. Now, it would be a much more interesting cup if we had a picture wrapped around it. Now remember, our cup is 4 units wide, but 4.75 units tall. So whatever picture we wrap around it, if we do a cylindrical wrapping, we want to keep the same aspect, but the width of the image should be 4 times pi. So here's a scene that I took, and I cropped the scene so that it has that particular aspect ratio. For example, I could have made the height of that scene 475 pixels and the width of it 1256 pixels. That would give the right aspect ratio so that when it's wrapped around the cylinder of the cup, it will keep the same proportions. So what I did here, I want to apply that image map for scene 3, use a cylindrical mapping, but I had to scale the cup down so that it's 1 unit tall. Therefore, I scaled the whole thing by 1 over 4.75 because it was actually 4.75 units tall. Applied the pigment map, the finish, and so forth. I also decided to rotate it -90 degrees in the Y direction so the seam there won't be right at the edge of the cup. And then I scaled it back up to its original size, 4.75. Let's take a look at this. Much better. A couple of things about the handle, and one of them is that the color red does not look very good here. I'd like to have a color that matches something on the cup. Another thing about it is that it's too cylindrical or too much like a torus. Maybe if we stretch it out in the Z direction, it'll look more like a regular handle of a cup. So let's see what we can do with the handle. That's the sphere sweep. Let's say I put a scale in there. I don't want to scale it X or Y direction, but I'd like to scale it in the Z direction. Let's say 2.5 units in the Z direction just to see what that does to it. Okay, see, it looks more like a handle now. I've stretched it out in the Z direction. So the only other thing I need to do is to change its color to match something here. Now, I went to my Photoshop program and I pulled up a color picker here, and I decided that a good color somewhere between the sky and the trees might be this color right here. And then I was able to read the color values from the Photoshop program, 51, 153, and 204. And in POV-Ray, instead of naming a color like red, green, or whatever, you can say RGB and put 3 numbers, but those numbers have to be between 0 and 1. The R stands for red, the G for green, and the B for blue. So the first number is the amount of red, the second number is the amount of green, and the third number is the amount of blue. But these numbers have to be between 0 and 1. On the color picker, they go up to 255. So if we divide everything by 255, we can specify the color in POV-Ray this way by saying RGB and this stuff right here. So for the handle, let's change that red to RGB, bracket, let's see, what were the numbers? 51 and 153 and 204, end bracket, and divide by 255 to make them between 0 and 1. And let's take a look at this and see how the handle looks. All right, see, that's a nice color for the handle. That pretty much does it for our coffee cup. We've got the color of the handle correct. We've got the scene wrapped around it, and the seam of the scene is over here at 90 degrees. So if we rotate this whole cup somewhat, we're not going to see that seam anywhere on it. Well, that's it for this lesson. In the next lesson, we'll look at triangles and polygons and some of the things that we can do with them to make other objects of our own choosing.